to the cloud. All right, so we're going to start with this battery, this electrochemical cell. We're going to use AU3+, so gold and zinc. These are the first two. The first part of the statement says, write the possible reduction half reactions for each beaker and reduction potentials for the cell. So we're writing out each of the half reactions as reduction reactions. So I'm going to write them up here. Kind of small, but I have a small pen. I'm going to take and look it up on the chart. Again, this is nothing I'm memorizing. I'm looking on that sheet of paper. I have aqueous, 3 electrons, yielding the solid gold, and the voltage is 1.50 voltage. Almost opposite. There you go. And then I have my zinc, which is my second solution, and I have zinc 2+, aqueous, and I have 2 electrons, and then I have zinc solid as my product, and its charge is negative 0.76 voltage. Then it says, select from A the half reaction that is most easily reduced. Okay, so that's part B. So the one most easily reduced, you'd have to look at the chart, and the one that's higher than the other is the gold. So I'm going to write down, because I'm going to put down that main information in the bottom, but since I'm just writing the small information, I'll squeeze that in up top. So 3 aqueous plus 3 electrons yields gold solid. And I'm going to put RED next to it just to remind me that's the reduced. Then it says select from these two the half reaction that's tougher to reduce. So if that's the case, it's going to be oxidized. And that will be as it is below on the chart from gold. And the chart is that potentials, the reduction potential chart is what I'm referring to. So I'm just going to write, I'm not going to flip anything just yet. I'm just going to write the equation as reduction, as is. There we go. So that is going to become oxidized because it's harder to reduce. So in part D, and this is where I'm going to bring it down because I do have to connect both of those together. So I'm going to bring this down a little bit further. I'm going to do D right here. So I'm going to take the information from the first two and bring it down over here into D, because it says reverse the appropriate half reaction from A, so that now you have a GER, gaining electrons, you're reducing, and you have a LEO, losing electrons, you're oxidizing. You have both of these half reactions, and then you combine them to make the entire reduction oxidation reaction. So let's do that right now. I'm going to take my zinc solid and reverse it. So zinc solid, I'm reversing it because now it's oxidized. And I have zinc aqueous ions and my 2 electrons. So I reversed it because this is the one that's oxidized. So this is a reduction, and I flipped it. And I'm going to take my gold and I'll write it as a reduction. So 3 plus aqueous ions. I'm going to bring it down a little bit here so you can see it better. And then we have our 3 electrons yielding gold solid. Because I reversed them, I have a different charge. This one wasn't reversed, so I'm going to keep that charge. And I'm writing this because later we're going to be asked to determine it. When I reversed the reduction portion and made it oxidized, I'm now going to change the sign to positive 0.7. I'm going to put a little oxidized just so we remember this is oxidized reduced. Okay, so now I'm going to bring this both together to make my redox reaction. So reduction, oxidation reaction, both of them together. And I'm still on D. So in order for them to be able to combine these two, I need to be able to cancel out these 2 electrons. So I need to balance this equation. Common denominator between those are 6. So to get 6 electrons here, I'd have to multiply by 3 for the entire equation. So I'll do that. And then I need to get 6 here. To get 6 here, I need to multiply by 2 for the entire equation. All right, so then part E says determine your voltage. So I'll take 0.76 and I'll add it to 1.5 and I get 2.26 voltage, and it's a positive spontaneous voltage. And then part F brings us to here. It says, hey, do the shorthand. The shorthand is easier for chemists to use and look at. So I didn't even finish the redox reaction, so I need to go back and finish that because I didn't combine them. So let me combine them quickly. Zinc solid plus 2 gold aqueous yields 3 zinc aqueous. And oops, I'm running out of room because I wrote that here. 2 gold solid. Again, the products can be written either way as long as they're on the product side. Reactants can be written either way as long as they're on the reactant side. So here's my redox reaction that I forgot to draw because now I need to make a shorthand. When you're making a shorthand, you're focusing on the reduction oxidation. So I'm going to do oxidation first just because I want to. I'll have zinc solid and it's oxidized. So now I'm going to have zinc aqueous. And then in the second container, I'm going to have gold. I'm going to have gold aqueous 3+ with gold solid. Okay, so when I'm looking at them separately, I then can see that one is being reduced and one is being oxidized just by what's happening. Remember, you're losing electrons or you're gaining electrons. Make sure so back to the recording. So we don't need to add the coefficients in our shorthand. You can erase that. So the shorthand does not include the coefficients. The next portions are now going to show information from the actual diagram. So I'm going to bring the diagram up. One thing we need to label is what are these two? So we've already gone through the work to determine what they are, so we can write them in here to know the flow of the electrons. So we have gold, and it is reduced. When something is reduced, it's called cathode. It has a plus charge. And zinc is oxidized, and it is called the anode. And it is a negative. Electrons move from negative to positive. So I'm going to show that by drawing through the wire. The electrons are actually moving through this metal wire in this direction. So note that these are electrons. I'll clearly show that there is movement by arrows. So my electrons are moving in that direction. I also have, so I've labeled that, I've shown the movement. I also have stuff happening here, right? I have this thing that's called the salt bridge. And I didn't label what ionic compound it is. So if you want to do an ionic compound that's sodium chloride, so aqueous sodium chloride would be +1, -1. I do ask you which movement, like where does it move? Where do those ions go? Well, let me mark it off here. So the positive goes towards the positive side. I'll use a different color. We have a negative, goes through the salt bridge to the negative side. I'll mark that there so it's clear as well. So we have the salt bridge, the ions moving, the electrons moving here. So as the electrons are moving here, they're being taken away and they're moving through. This is now going to show a voltage or a light bulb if we hook that up. But what's happening with the, right? And then from the information here, we have the electrons moving. So let's see what's happening with this piece of metal. As the electrons are moving away here, this portion of the metal starts to flake off. And actually, then there's more zinc ions that are forming. So I'm going to draw an arrow, like when it asks what's happening to the movement of ions in the beaker, these are coming down into the solution, because this little breakaway means that part of that piece is actually breaking away because of the fact that their electrons are losing. At the same token, gold, on the other hand, is gaining electrons. So because it's gaining, I'm even going to show that by adding it on and saying that now the ion is actually gaining into part of the gold. So I'll note that by writing it. The gold mass is being added to the gold metal. I don't know if that makes sense, but they're adding that into the gold metal. And here, your zinc metal flakes off, I call it, flakes off. Because yes, you now have it in aqueous form, versus this one, the solution form then goes to the metal. So you're actually gaining the metal on the end. All right, so that's describing what would happen to the mass of each of these electrodes. And just a reminder of the vocab, that piece of metal is called an electrode. I didn't make sure we point that out because that is in the question. So no, this is an electrode. When we're talking about electrodes, those are electrodes. All right, I'll stop my recording.